Hello and good morning, good afternoon, or good evening to everyone. Thank you so much for joining us for another Safeopedia webinar. My name is Samantha, and here at Safeopedia, it is our mission to support you, the EH&S professionals, operational folks, and any safety-minded individuals with free safety information, tools, and education. I want to extend a huge thank you to all of you for joining us today, as well as our dedicated safety professionals for the great work they do on a daily basis in keeping our workplaces safe. Today, we are proud to present Beyond the Beep, real-world gas detection strategies for the oil and petrochemical work sites. The Safeopedia webinar has been made possible today by GFG Instrumentation, Inc., a preferred manufacturer member of AD Safety Network. AD, together we win. It is now my pleasure to welcome back today's presenter, Bob Henderson. Bob is going to give you an in-depth session focused on real-world challenges of gas detection in the oil and petrochemical industry. With that, Bob, let's jump into it.
Hey, everybody. Thanks for signing on. It's a pleasure to be here yet again. I love having a chance to talk about gas detection issues and concerns for the oil and petrochemical industry. If you're in the gas detection manufacturing business, this is a big part of your customer base and your orientation. It's a challenging category of gas detection. There is gas detection going on in this part of the industry 24 hours a day. So here we go. Now, the nature of today's seminar, it's very brief. Exactly how much you can do in 1 hour is a little bit problematic, but what we're trying to do is to provide an overview of gas detection issues and answers from the perspective of workers, employers, contractors, emergency responders, and especially to provide a framework for assessing gas detection needs. If you're evaluating a new type of instrument or making a change or upgrading your existing equipment, what questions should you ask? What issues should you consider? What is the best or optimal gas detection solution? And always, this stems from the idea that asking better questions leads to better solutions and to better responses for your company. At the end of the day, the fitness for use of whatever you're using now or whatever you intend to use in the future, fitness for use is a function of the sensing technology and the manufacturer purpose. I love this picture. And actually, what you see in my position is a lot of instruments that are wonderful products from many manufacturers that are being purchased and turn out to be unfit for purpose after the fact. What you don't want is to buy an Asian carp instead of a friendly, dependable, easy to use, loyal and dependable porpoise. So remember, the idea here is to choose the right porpoise, if that's not too strained. We always want to make sure that we look inwards in your company's programs. Have a look at what you're doing now. What are your most urgent needs? What are your urgent concerns and problems? The better grasp you have of the activities and risks that are currently going on with your gas detection program, the better. Drill down, make sure you understand what's most important. Make sure you're meeting all current requirements. Requirements have a way of changing. Where do you need to make improvements? Gas detection issues, by the way, are not necessarily limited completely to safety. There are all sorts of other duties and requirements that involve the use of gas detection equipment. And also, gas detection solutions are definitely not limited to portable instruments. Often, they include fixed gas detection systems as well as portables, sometimes both, sometimes predominantly one, sometimes predominantly the other. Types of gas detection requirements include personal protection, industrial hygiene, exposure assessment, Sometimes it's driven by community noise, community requirements, such as nuisance order or fence line systems. Sometimes it's regulatory courtesy of the EPA. It's not always courtesy of OSHA. Sometimes it's disaster response. Sometimes it's special gas detection requirements that are associated to specific projects or shutdowns. Often it is related to confined space entry at an oil or a petrochemical facility. Confined space entry is just going on all the time. It's constant. You have routine entries, you have large scale ongoing entries during shutdowns, you have sometimes in vessel entry into inerted vessels where the atmosphere has been replaced with nitrogen or some other inerting gas. Hot work in confined spaces adds a whole additional layer of concern and issues, and sometimes other special procedures like catalyst rebuilding are going on in confined spaces. So confined space activities are a big deal in the oil and petrochemical industry. So, what are the dominant atmospheric hazards? Well, the basic four hazards are always there. You have oxygen deficiency and oxygen enrichment. You have the presence of toxic gases, especially the potential presence of H2S. You have the potential presence of combustible gases. Also, often you have the presence of VOC, volatile organic chemical vapors. These VOC vapors are combustible if they reach a high enough concentration, but they are toxic at a much lower concentration. The atmospheric monitors that you typically are going to find in use are a lot of H2S single gas instruments, a lot of four gas instruments that include explosive gas, LEL, oxygen, CO, H2S, a lot of five gas instruments that include a PID, a photoionization detection sensor for VOC measurement at ppm concentrations, and often you have a sixth or even a seventh channel of measurement, depending on what else is going on and whatever other hazards are a specific concern. Invariably, in a multi-gas instrument, one of the sensors is going to be an LEL sensor. There are several different varieties of LEL sensors available, and choosing the correct LEL sensor is really critical. Some of them are going to work, some of them may not work for your specific application. They all have, each type of LEL sensor has specific advantages, but also disadvantages and limitations. So you really need to consider how you are going to measure the combustible gas. And I'll just briefly talk about the three major types of combustible gas sensors that are available for use in portable or fixed gas detection instruments. The most common is still the traditional catalytic Wheatstone bridge type sensor. These sensors detect the gas by oxidizing the gas. With oxidation, you take a little more power. You have a bead that's heated to a high temperature in the sensor. In the presence of gas, the bead increases in temperature because of the oxidation or burning on the actual surface and inside of the bead. Infrared LEL sensors are lower power. They have the advantage of being a better sensor for very large molecules, which are often the majority of the molecules that you're trying to measure if you're measuring crude oil or diesel or jet fuel. And you have another type of sensor called molecular property spectrometer sensors, or MPS sensors, where they're looking at the density of the atmosphere. In fresh air, the density is going to be lower than if you are in the presence of lighter than air combustible gas, or the density will be heavier than fresh air if you're in the presence of heavier than air gases. So the most common type of LEL sensor by far is the traditional catalytic LEL sensor. The advantages are it's very predictable, well understood technology, predictable cross sensitivity, and most instruments that in multi-sensor instruments that include a catalytic LEL sensor have a built-in library of correction factors. So you can change the measurement scale from natural gas or methane to pentane, if that's a more appropriate gas. If you're at a refinery, a lot of times the gases that you're going to be measuring are closer to pentane or hexane than they are to methane, so you can switch scales. Disadvantages are it uses a little more power than the other kinds of sensors. It has a poor response to larger molecules, a slower response to larger molecules. Very importantly, you can poison it by exposure to certain sensor inhibitors or poisons. The top of the list of sensor poisoners would be silicone, vapors that contain silicones. It has a requirement for the presence of oxygen in order to detect gas. If you have less than 10% oxygen in the monitored atmosphere, then your readings may not be fully accurate. Another really important thing about the catalytic LEL sensor is that it is capable of being used to measure acetylene and especially hydrogen. Hydrogen is pretty common out there. So if you have the presence of hydrogen, you need to do something to measure it. You can measure it with an electrochemical sensor, or you can measure it with a catalytic LEL sensor, but you're not going to be able to measure it with an infrared LEL sensor. Advantages of infrared LEL sensors are they can't be poisoned. They don't require oxygen to detect gas. As I mentioned, they use less power. They respond really well to large molecules. The more carbon hydrogen molecules in the molecule, the higher the response. So you actually get a larger signal from, say, a hexane molecule where you have 6 carbons in the molecule, and a higher response than you have with a methane molecule where you have 1 carbon and 4 hydrogens in the molecule. Disadvantages are the molecules have to be able to absorb infrared light. That's how you're measuring the molecules. You're shining a beam of infrared light through a sensing chamber, and you're looking for absorbance. And hydrogen does not absorb infrared light. That's why you can't measure hydrogen at all. And acetylene can absorb infrared light, but not at the wavelength that you use in portable instruments. So with portable instrument IR LEL sensor, acetylene is also invisible, which means you're going to need to measure it with a different type of sensor, like an electrochemical sensor. Different IR-LEL sensors have very different performance characteristics. You should talk to the manufacturer or read the manual of whatever instrument it is that you're considering if you intend to utilize an IR-LEL sensor. Make sure it does the job. There are some IR-LEL sensors that are great for methane, but they're not very good for aromatics or unsaturated hydrocarbons like cumene or toluene or other VOCs. So you do have to be careful about that. The third type of commonly used LEL sensor is the MPS sensor. Actually, it's kind of a misnomer to call the MPS sensor an LEL sensor. You can use it to measure LEL gases, but you're not actually measuring flammability characteristics of the molecules. What you're doing is looking at the density of the mixture of gases in the monitoring zone, in the monitored area, and you're seeing how different it is from fresh air. If the density is different because the additional gases that are present are lighter than air, you interpret the readings as an indication of the presence of a lighter than air combustible gas like hydrogen or ethane. If the atmosphere is heavier than fresh air, you assume that the difference is due to the presence of heavier than air combustible gases like propane or pentane or hexane or octane or any of the larger molecules. It's a dependable technique as long as you don't have something else going on in the background that changes the ratio of the molecules that are normally present in fresh air. In fresh air, you normally have 20.9% oxygen. The balance over 79% or thereabouts is nitrogen. And as long as that ratio stays the same, then the MPS sensor can easily tell the difference between fresh air and the presence of something else. But if you happen to have another gas that is present, like carbon dioxide is much heavier than air. It turns out that if you have an oxygen deficiency, most of the time, the oxygen deficiency tends to be due to the presence of carbon dioxide. The exposure limit for carbon dioxide is 5,000 parts per million. That's the 8-hour TWA. Well, if you have 2,100 parts per million of CO2, that's not even one half the TLV, not even one half the permissible exposure limit for carbon dioxide. That is the same exact density as 10% LEL propane. So you can see how that can cancel out the ability to pick up a lighter than air gas, or if you have the presence of the carbon dioxide along with some heavier than air gas, your reading is going to be inaccurately high. So high or low, you can easily have an erroneous reading. So for me, I don't recommend using MPS sensors for confined space entry. Carbon dioxide is just too pervasive a potential hazard. And by the way, when you have carbon dioxide in a confined space, you should be measuring it on a direct basis when possible. If you're confined spaces in the oil industry, there's often carbon capture going on. There's a lot of CO2 increasingly that's present. Where CO2 is present, then remember to include a direct reading CO2 sensor in your multi-sensor instrument. As I mentioned, I think I mentioned, still today, the most numerically prominent or predominant type of instrument continues to be a single gas personal H2S meter. These are still very dependable, widely used, very simple. You turn them on, they take very, very little power to operate. They are based on a substance-specific electrochemical sensor that is designed to measure H2S. By the way, it's an H2S sensor. It's not an SO2 sensor or a mercaptan sensor or some other kind of sulfide sensor. It really is designed to show very little response to other sulfur-containing molecules. The idea is to have a highly accurate sensor for H2S measurement. If you have a source of sulfur. Why is H2S so prominent in the oil industry, production and refinery and transportation and pipeline, whether it's production or midstream or refineries? H2S is out there. It's very common. It's produced by anaerobic. They don't use oxygen, sulfate reducing bacteria. These anaerobic bacteria, instead of producing carbon dioxide as their metabolic byproduct, like humans and higher animals, uh, they produce H2S as their byproduct. The higher the sulfur content, the greater the potential for H2S. Older fields that have been well inoculated with sulfur fixing bacteria tend to be more prone to producing H2S than brand new fields. It's once the H2S producing bacteria have been introduced, inoculated into the geology, then they're down there doing their business slowly but surely. So if that field is 100 years old, they've had 100 years head start for H2S production. It's heavier than air. It collects in vessels, pits within protective berms, other low-lying areas. It persists for quite a while in air. Eventually, sunlight can break it down, but it can take a while. It's extremely toxic. 1,000 parts per million, a single breath will result in knockdown. You will lose consciousness immediately, and unless somebody hauls you out and provides CPR to get you going again, you're not going to make it. So take it very seriously. Now, H2S, the sensor is good for H2S. It's not good for other types of hazards. If you have a second hazard that's present, for instance, if you're manufacturing mercaptans, you might need a two sensor instrument. You don't go automatically always from one sensor to 4, 5, or 6 sensors. A lot of applications, you have two monitoring requirements. If you are doing hot work in an environment that might potentially be associated with H2S, then you certainly have SO2 as a potentially present hazard. So having an H2S and C and SO2 sensor in a two sensor instrument is a very nice solution. So you don't always need two sensors, but when you do, they are available. And there are a lot of unique combinations where one hazard kind of goes along with another hazard, or where you need to look at the two hazards at the same time. In the fire service, a lot of times the two hazards that go most commonly together are cyanide and CO, or CO and HF. But whatever the combination, if you need it, you can ask for it, and manufacturers are often going to be able to deliver. The backbone of oil industry instruments does continue to be a four-gas instrument like the one that you see here, which is one of our own products. It's a GFG G450, where you have oxygen, CO, H2S, LEL, and that's it. It's simple, cheerful, simple to use. Sometimes you need more than that, as we've discussed. The G888 has the ability to measure a couple more hazards. So you could add carbon dioxide and SO2, or carbon dioxide and NO2, but we have a lot more opportunities for measurement of additional analytes or gases. And the third option would be a pump-equipped instrument. You can either have a basic diffusion instrument where you take the instrument into the area where the hazards exist, and the hazards simply diffuse into these sensors, Or you can equip the instrument with a mechanical pump. When you turn the pump on, you're pulling the sample in through a hose and probe assembly. We'll talk more about that in a minute. If you have the presence of alcohols, heavy fuels, volatile organic chemicals, you're going to need a fifth sensor, and that's going to be generally a photoionization detector sensor or a PID sensor. PID-equipped instruments are by far the best choice for the measurement of VOCs at exposure limit concentrations. For most VOCs, long before you reach a concentration sufficient to register on a combustible gas sensor, you will have already exceeded the toxic exposure limit for the contaminant. This is especially true for VOCs such as benzene, toluene, xylenes, phenol, cumene. So consider including a PID in any multi-gas instruments used for fuel spills or other situations that involve VOC vapor. A lot of confined space entry programs will make initial use of a 5-gas or a 6-gas instrument with a PID sensor once you have verified that the environment is free from VOC hazards. Then you can step down to a 4-gas instrument. So you don't necessarily have to have 100% of your instruments equipped with a VOC sensor. But at the very least, if you have the potential for the presence of VOCs, make sure that you take your initial readings with an instrument that includes a VOC sensor. Here's an illustration of how much you miss if you're trying to get by using only an LEL sensor. In this table, I have the contaminant in the first column. I have the LEL concentration. I have the exposure limits, and I have, just to be extra super conservative, I'm not setting the alarm at 10% LEL, which you would normally do, even if I set the alarm at 5% LEL, but I'm just recalculating 5% LEL in ppm. So for acetone, the OSHA PEL is 1,000 parts per million, but 5% LEL is 1,250. For ethanol, the PEL is 1,000 parts per million, 5% LEL is 1,650, and so on and so forth. Each block in this chart where you see red is a analyte is a chemical where 5% LEL is higher than the exposure limit, and sometimes a lot higher. The only time where that is not the case, is when OSHA hasn't gotten around, or NIOSH hasn't gotten around to publishing an exposure limit for that chemical. If they did, the same would be true for that chemical. For diesel, we'll be talking about the diesel TLV in a few slides here. The TLV is 15 parts per million. 5% LEL is 300 parts per million. That means even if you set the alarm at 5% LEL, even if the sensor does a good job of detecting the diesel vapor, you're exceeding the toxic exposure limit by 20 times if that's where you're setting the alarm. So that's really not acceptable, and that's why for VOCs, because of these toxicity issues, you really do need to include a PID sensor. LEL and PID sensors are broad range sensors. They are non-specific. The PID, just like the LEL sensor, provides a single reading that comprises the effect on the sensor of all of the detectable gases that are present. So all of the combustible Gases are going to affect the LEL sensor. The detectable ones are going to affect the LEL sensor. You get one reading. For the PID, the way the PID detects is you shine a beam of ultraviolet light through a sensing chamber and you ionize the target molecule. You strip an electron. That produces an electrical current that is proportional to the concentration of gas. And you can have a mixture of many kinds of gases. You get one electron from each of the molecules that's present at that moment in the optical sensing chamber. So you get one signal for the entire mixture of VOC gases. So it's a broad range sensor. The sensors cannot distinguish between different contaminants they're able to detect. The readings are always going to be relative to the gas that is used to calibrate the detector. So if you calibrate the combustible LEL sensor on methane, the readings are in methane units of measurement or pentane scale units of measurement. For PIDs, most generally, you're going to calibrate the instrument to isobutylene. So the readings will be given in isobutylene scale increments, ppm isobutylene equivalents, or sometimes in the display we will say PID units, and the PID unit is set by the gas you use to calibrate. LEL and PID sensors are complementary detection techniques. That is especially true when the instrument is equipped with catalytic LEL sensors. CCLEL sensors are excellent for the measurement of hydrogen, methane, ethane, and other common combustible gases that are not detectable by PID. PIDs, on the other hand, are excellent for measuring toxic VOC and larger hydrocarbon molecules that are less detectable by combustible catalytic LEL sensors. And PIDs are optimized for use at ppm and sub-ppm exposure limit ranges. PID sensor limitations are not PIDs are not certified for LEL measurement and should not be used for LEL measurement. To make sure if you need an LEL reading that you have an appropriate LEL sensor. The best approach in a multi-sensor instrument is to have both a LEL sensor and a PID sensor in the same instrument and any other sensors that you might need to measure specific gases of interest. PIDs are providing readings that are relative to the gas used to calibrate the instrument, calibrate the PID. But if you want, you can make the reading specific to the gas of instrument. And the way you do that is by choosing a correction factor. The correction factor is what the instrument will use to multiply the actual reading to come up with the true concentration. In most PID equipped instruments, you have an extensive library of correction factors. So if you know that you're dealing with toluene, you can simply choose toluene from the library and your reading will be, actually it's not going to be that much different than the reading for isobutylene scale. But you can choose the toluene scale and it will exactly calculate the reading for toluene in true toluene increments or units of measurement. But there's one limitation to this approach. Correction factors are approximations. They're pretty good, but they're still approximations. And they can change a little bit over the life of the sensor or as a function of ambient environmental conditions, like changes in humidity. So take the correction factor reading with a slight grain of salt. In other words, be conservative. Don't go right to the limit. Be conservative. Leave conservatively and early. Don't stay unconservatively later on in the area. When the alarm goes off, leave immediately. And most manufacturers do provide, besides the built-in table of correction factors, you also have technical notes or other resources from the manufacturer with a more extensive list of detectable chemicals and correction factors. Don't use somebody else's table of relative responses and correction factors. Use the one that your manufacturer has provided for your instrument because the readings are going to be a little bit different depending on the manufacturer until you provide the correction factor. And the correction factor will make up for the differences, but they won't make up for the differences if you use the correction factor for the wrong manufacturer on your readings. The lower the correction factor, in other words, the less that you need to multiply the reading to come up with the true concentration, the higher the sensitivity has, the PID has to that gas. So a low correction factor is a good thing. That means the PID has higher sensitivity to that gas. The more toxic the gas, the more important it is to have a low correction factor. If the exposure limit is less than 10 parts per million, you should hopefully have a correction factor of less than or equal to 1. If the chemical is less toxic, you can have a higher correction factor. If exposure limit is greater than 10, the correction factor could be up to 10. If the correction factor is greater than 10, now you're talking about having a sensor that is better used as a gross leak detector. It's not going to give you much in the way of an analytical response. It's a much more qualitative response. And this is why you don't want to use some other manufacturer's table of correction factors interchangeably with a different brand of instruments. If you look at the correction factors for ammonia, for Ray, 9.7, BW 10.6, Ion Science 8.5, GFG 9.4. So you can see there's a pretty good spread. For butadiene, here's another one with a wide spread. Correction factors range all the way from 1 to 0.7 or 0.69. As long as you know what the correction factor required is, all of this comes out in the wash because the instrument is normalizing the readings to come up to the true concentration. You just don't want to use the wrong table for the wrong instrument. So stick with the materials that came with your product. Now, a special concern in the oil and petrochemical industry is benzene. Benzene is definitely the most toxic of VOCs that you're going to run into out there. There is no safe exposure level. Even tiny amounts can cause harm. And workers can be harmed with inhalation of benzene if it is present. Exposure to benzene increases the risk of developing leukemia, aplastic anemias, other blood disorders. It's naturally present in crude oil. It's a minor component in diesel, jet fuel, and gasoline, as well as engine exhaust. Other sources include everything from volcanoes to forest fires, brush fires. It's actually becoming quite a big deal for people that are fighting the catastrophic brush fires that we've seen in the last few years. Half of all exposure to benzene in the United States continues to come from cigarette smoking. So don't do that either. Benzene is a cyclic molecule, 6 carbons arranged in a ring, connected to hydrogen atoms. So there we are, uh, sailing through the air in psychedelic fashion. I love this animation. Takes me back to the 1960s. Uh, anyway, benzene exposure limits. One of the reasons that in the oil and petrochemical industry, there's so much concern at the moment about benzene is the 2024 TLV has dropped the exposure limit, the time weighted average, the 8-hour TWA to 0.02 parts per million. That is a big shift in the downward direction from where it used to be. Now, the OSHA permissible exposure limit, which is a TWA of 1 and a short-term exposure limit of 15 minutes Stella 5, that hasn't been changed. The NIOSH REL, the recommended exposure limit, that hasn't changed. It's as it was. It's still 0.1 ppm for the TWA and 1.0 for the STEL. The only thing that has changed is the TWA, the TLV TWA, which used to be 0.5, and the STEL is gone completely from the latest TLV. It's now a single part definition, and it's all the way down to 0.02 parts per million. And that's a challenging reduction, especially if you need to measure the benzene concentration on a substance specific basis. Now, whether you need to do that or not is a question that merits some discussion. It's pretty tough to do. It can be expensive to do. It might or might not always be necessary to do. What are the options for setting the alarms? Well, first of all, the question is, should you focus exclusively on benzene? Because benzene is seldom present by itself. Usually it's one of a crowd. You've got a bunch of other VOCs that are also highly toxic that are present at the same time as the benzene. If the only thing that you measure is the benzene, then you're missing out on a bunch of the other toxic chemicals that are present at the same time. Should you depend on the TWA alarm only? What about other toxic VOCs that are present? How should you set the instantaneous alarms? And is it possible to take action on total VOC if you know the fractional percentage of benzene, or are there some other TLVs that you can use that will make your life a little bit simpler? These are all things that are especially if you're in the safety office or the industrial hygiene office at your facility, these are important issues to discuss. So benzene is a minor fraction generally of the total VOC concentration present. When the combustible liquid has an established permissible permissible exposure limit, or TLV, it would be permissible to take action based on TVOC and set your alarm at the, say, the diesel TLV limit. The TLV is designed to be protective for all the stuff that's in the diesel vapor, not just the tiny fraction of vapor that is due to the presence of benzene. You have a TLV for diesel, you have a TLV for kerosene, you have a TLV for JP8, jet fuel, you have one for gasoline. You know, it's a lot easier if you're taking action for total VOC at 15 ppm than it is to try to take action for benzene only at 0.02 ppm. So if your source of contamination has a TLV, This is a really good shortcut to monitoring and keeping your workers safe. If you exceed the TLV for diesel, then what you would do is to make sure that you have not exceeded the benzene limit somehow, you can always do a substance specific confirmation test using a different kind of monitor. Use your for initial sampling, use your broad range PID with an alarm setting of 15 or even higher. A lot of alarms are set at the initial alarm is set at up to 50 parts per million TVOC, and that can be very safe. Um, but if you need to confirm or deny the presence of benzene at the TLV, then you can use a substance specific benzene detector. Now, this is a lot of words in this slide. I don't like slides with a lot of words, but the words in the case of this slide come directly from the TLV guide published by the ACGIH. Those are the folks, the Association of um, Government Industrial Hygienists. These are the guys that come up with the TLV recommendations. And right from the book, it explains the science behind the TLV and how to set the alarms. The TLV doesn't tell you where to set the alarms. It gives you a maximum recommended exposure limit. In the case of the benzene TLV, it's a one-part definition. It's an 8-hour time-weighted average of 0.02. It doesn't tell you where to set the instantaneous alarms. Sometimes people think, well, if the TWA limit is 0.02, I have to set the alarm, the peak alarm, the instantaneous alarm at 0.02. Well, no, that's not what it actually says in the fine print of the TLV. It actually, in the fine print, says you can set the alarm, or the way that it's expressed is you shall not set the alarm higher than 5 times the TWA. So actually, if you have 0.02 as the TWA, you could set the instantaneous alarm at up to 5 times that value, which would be 0.1 part per million. Again, that makes it a little bit easier. So remember that when you're setting the alarms, you have some latitude. You don't have to set the instantaneous alarm at the TWA limit. This recommended or allowed procedure or guidance is for gases and vapors that have a TWA limit, but that don't have a ceiling or a STEL limit. Uh, but for many of the most common toxic gases like benzene, if you look at the TWA, at the TLV handbook, you'll see their single part definitions based on the TWA. As I mentioned, benzene is just hardly ever there by itself. What are some of the other, just to put this in perspective, what are some of the other toxic hydrocarbons that are present in crude oil? And they're all toxic. Hexane, lots of hexane around. TLV, 50 ppm. Toluene, lots of toluene around. TWA is 20. Xylene, lots and lots of xylenes and isomers of xylene, 20 ppm TWA. Ethylbenzene, and you can see here is in each of these molecules, you see the benzene ring, that's the basic molecule, and then you have additional chemical groups that are stapled on. So for toluene, you have this CH3 group. For xylene, you have two CH3 groups. For ethylbenzene, you have a two carbon group. For cumene, it's a it's a an alkyl group, so it's got the same group that you would find in an alcohol molecule. For phenol, it's this three carbon group that is stabled on. And when you're talking about cumene or phenol, holy smoke, you know, the exposure limit is 5 ppm. That's dang near as toxic, or it's in the same ballpark toxic, certainly as benzene. Remember, the OSHA for benzene is still 5, so 5 and 1. So it's pretty dang toxic. Now, for diesel, the reason the TLV works at 15 parts per million is because such a small fraction of the diesel vapor comes from benzene. The content, benzene content in diesel is typically less than 0.02%. So if all you're measuring is benzene and you're ignoring the rest of the VOCs in the diesel vapor, or you're just dealing with it from the standpoint of LEL combustible gas, you're omitting the measurement of 99.98% of the toxic VOCs that are present. So when it works, I'm a strong proponent of taking action, initial action, on the basis of TVOC. I am happy to take a substance specific reading for benzene any of the time that it is necessary, but I like real-time continuous TVOC readings, and I like to use a multi-gas instrument that has a PID sensor for that purpose. And usually I'll set the alarm depending on what it is that I'm measuring. The alarm might be 15 or 30 or 50 parts per million. If I have a hit on the TVOC alarm, that's when I come back and test substance specific readings for benzene. The same goes for gasoline. Gasoline has a higher concentration of benzene on a fractional basis, but it's still less than, well, no more than 1% of the gasoline vapor is due to benzene. So setting the alarm, TVOC alarm at 300 ppm for gasoline is still pretty safe. There are a lot of developments and new types of gas detectors. You're going to be tempted to have a look. And there are new procedures, new requirements, new products, new sensors. Wireless communication is a big deal. Third-party support through call sensors is a big deal. So here's a few questions you should ask if you are planning to update, expand, replace, or change the equipment that you're currently using. Before making a change, make sure you understand what's going on behind your back at the moment or in front of your back. If you're not sure, drill down, and talk to people. Have a discussion with people who are using instruments about how they're doing. Ask the manufacturers or distributors of the products you work with for their thoughts. Manufacturers are full, they're full of stuff sometimes, but they're also full of knowledgeable people if you can get to them, who can answer questions and give you a good helping hand. Discuss the ways the manufacturer and distributor can help meeting your needs and give you a few alternatives. The starting point is always to Make sure you understand how your current equipment is performing. Are you happy? Are you having problems? How old is the equipment? How out of date is it? What features have you heard about that are of interest? What brands or models are you considering? What are the alternatives? Distributors are a great source for product information, especially the ones that belong to affiliated AD, the AD organization, affiliated distributors. They're in business to provide value added service and knowledge. And even if you don't know who to call at the manufacturer, they will. So seek your local AD salesman out. He or she is a tremendous resource. Avoid, at least initially, being overly focused on price. Eventually, the decision proceeds on the basis of price and affordability. However, there is a big difference between the initial purchase price and the true cost of ownership. If the product you buy doesn't work the way it's supposed to work, then it doesn't matter what the price was, high or low, you just wasted a bunch of money. This questioning process is designed to uncover your needs and what will provide the optimal solution. Cost of ownership issues, you know, if you buy an inexpensive instrument, but you're spending a lot of money to keep it going, or if calibrating and servicing the product is problematic or expensive, then again, you didn't get a good deal. So are you questions to ask? Are you spending a fortune on your current equipment? Are you being charged a monthly fee? Do you trust your gas detectors? Are you having a lot of sensor failures or battery problems? Do you do your calibration and service yourself and maintenance yourself, or do you farm it out? Is it expensive to keep it in proper working condition? And remember, you're expected to maintain that instrument according to manufacturer requirements. So whatever the manufacturer says in the manual, that's your burden. That's your obligation. And when it comes to periodic testing and calibration, OSHA is pretty firm. The NFPA is equally firm. CSA and UL are also very firm in their recommendations or requirements. You're supposed to perform at a minimum a qualitative bump check before each day's use. That's simple to do. It's just exposing the sensors in the instrument to gas above the initial alarm concentration. And when you flow the gas, you make sure that the alarms are activated. Periodically, you want to perform a full calibration. How often you do that depends on what the manufacturer says. But if you fail a bump check or a calibration check, then you need to perform a full calibration before you put the instrument back into service. You also, in a confined space entry program, have to determine how you are going to sample the atmosphere in the confined space before you go into the confined space. That means generally being able to pump a sample. Another really important consideration is the kind of batteries in the instrument. If you have lithium ion batteries, God bless you, but those are hazmats, and there are liabilities as well as benefits to that battery technology. If you're considering a wirelessly enabled instrument that can communicate to a remote location, that's again something else to think about. What about after the sales support? Whatever you buy, you're going to want help at some point over the life of the instrument. Maybe it's a sensor replacement, maybe it's training, maybe it's something else, maybe it's just advice. What does this strange reading mean? After the sales support matters, you deserve excellent after the sales support. And at least with the affiliated distributors network, with AD and GFG, we are here to help. We have great products. We have tremendous great distributors, great support, good resources. Go to the website, in our case, GFG Inc. GFGsafety.com is the website. We have application notes, webinars, training videos, everything that you might need to get the most out of your instruments. And it's www.gfgsafety.com/USEN. Make sure you put the USEN at the end. That way you'll get to the North American US version of the website. That's where we have all of the support materials for the North American version of the products. So thank you for sitting in on the webinar. I hope you'll call in later on with questions. I am here to help. Just drop me an email. We will get back to you as soon as we can. Thank you very much again, and be safe. Bye-bye.
Well, thank you so much, Bob. That was a lot of really important information, but a lot of really cool information. So I want to thank you again for your time and your extensive knowledge. And again, as Bob mentioned, his contact information is on the screen right now. Head on over to GFG Safety, reach out to Bob, email him, get in touch. Make sure that you're getting all of those questions answered so that you can stay safe. So Bob, before we wrap it up today, is there anything you want our audience to take away or keep top of mind so that they can stay protected?
The best advice I can possibly give you is use your instruments. People that use instruments don't turn up in accident reports. Accident reports generally involve people that were not using their gas detector at the time the accident occurred. So that advice, beyond all else, whatever you buy, whatever you have, use it, stay safe. It's a very important tool for your welfare. And thank you again.
Perfect. Bob, again, a huge shout out to you. I want to thank AD Safety Network for allowing you to be here today. And of course, I want to thank all of the dedicated safety professionals for the great work they do on a daily basis in keeping us safe. Reach out to Bob, reach out to your distributors, and use your equipment. Take care. Stay safe, everyone.